For this review of inheritance mechanisms, there's one more case and one more construct that we need to see having to do with repeated inheritance, which is also sometimes known as the diamond structure. So consider a situation like this, which really will arise as a result of multiple inheritance every once in a while. We have a notion of university member, and a university member has an ID. This class might have many other features, but I'm taking just one feature as an example, ID. Then there are two kinds of university personnel, a teacher or a student. And then you see where we are heading. A teaching assistant, or just assistant in the figure, is someone who, from certain viewpoints, is a teacher, but from other properties, really is a student. And he or she really has properties from both sides, which means that if we make assistant using multiple inheritance inherit from both teacher and student, then assistant will also be a descendant, remember this term descendant meaning heir but direct or indirect, of university member. So this is a case known as repeated inheritance, also known as the diamond structure. It's often confused with multiple inheritance. Multiple inheritance is the simple case and the usual one in which we simply have a class inherit from both. Repeated inheritance is the special case in which, as a result of multiple inheritance, a class may be a descendant of another class, like assistant from university member, through more than one path. In this case, the path on the left and the path on the right. So we're going to see how to deal with a repeated inheritance. First, let's know that repeated inheritance can be indirect, as in the previous case, where D inherits multiply from A through B and through C. There could be, of course, many more intermediate levels, but we are also going to allow, strange as it sounds, D to inherit from A directly several times. In fact, you can have a class D which has a clause inherit A and then another clause inherit A. That's going to give us the picture on the right. You might ask, why would anyone ever do this? Well, there are only a few cases in which it could be useful, but still it's permitted by the language, so we have to know what it means, what the semantics is. Much more common cases, and completely realistic ones, arise in any object-oriented language in which you have multiple inheritance, but you also have the notion, as in Eiffel or in Java, or of a top class. In Java it would be called object. In Eiffel it's called any. Now Java does not have multiple inheritance as we have seen, but Eiffel does. The general idea is that any class whatsoever is a descendant of any. This is achieved simply by saying that if a class does not have an explicit inherit clause, like maybe C has, like maybe C does, no inheritance clause, then it's considered to inherit from any, otherwise it will inherit from any through its explicit parents. So what's important here, as suggested by the dotted lines, is that any class like C or list has any as its ancestor. The lines are dotted, by the way, simply to suggest that the inheritance between list and any, for example, could be direct or indirect. That's what the dotted line means. It means ancestor rather than direct parent. So as soon as we have multiple inheritance in such a scheme, then because all the classes that serve as parent, in this example list and C, are descendants of a common class any, it means that multiple inheritance implies repeated inheritance. And so we are going to have a possible problem if some of the features have been redefined. Assume, for example, that list, and this is indeed the case, has its own version of copy and its own version of the equality comparison. Actually, this is indeed the case, since when we copy a list, we don't just want to copy the list header, that's where the list object is, but typically a list, for example, a linked list, is going to have other objects that represent the list. So the list object per se, or at least linked list, but I'm using list here for short, is just the header. And if we just had the standard copy, which comes from any, then copy would just copy the list header. But for list, what we really want to obtain when we copy a list is to copy everything, including the list elements. So if you look up classes like linked list, you will see that they indeed redefine copy to copy everything, and same thing for equality comparison of two lists, which doesn't just compare the list headers, but their elements. Let's assume that C has not redefined copy and is equal. So the question in D arises of which copy and is equal we are going to use. Do we use the version from list or the version from is equal? On the surface, this is just a normal name class. We have copy on the list side, which has been redefined, and we have copy on the C side, which has not been redefined. So we have a name class, and we should remove it. And so the first step is going to apply the renaming technique, which we have been using before. However, this is not going to be the end of the story in that case, as we're going to see, because of polymorphism and dynamic binding. So we have seen what an acceptable name class was, and now we are going to see another case of acceptable name class, which is the case of sharing. So let's assume that we have the situation shown here. A has F and G has been renamed in respectively B and C. It could have been renamed in just one of these, either B or C, but for symmetry I'm renaming them on both sides. On the other hand, F has not been renamed. So the question here, the first question that arises is, at the level of D, the repeated descendant, do we have in each case one feature or two features? And here the answer follows directly from the principle that I've emphasized a few times, the principle that there is a mapping between feature names and features. And so one feature name, one feature. Well, as a consequence, F, which has not been renamed, only has one name in D, and so it's going to be one feature. Any feature not renamed along any of the inheritance paths will be shared. Shared meaning there's only one feature. On the other hand, G is inherited under two different names, and so it should correspond to two features. It's always the same thing. This very general and simple idea that to one name there should correspond at most one feature in a class. This is, however, not the complete answer. There's still an element missing, because here we have considered only renaming. What about redefinition? This case appears very clearly in our fictitious example of a class D that inherits from both list and C, where a list has redefined copy and is equal. So with what we have seen so far, it's enough to remove any ambiguity, except in the case of a polymorphic assignment. Let's assume that we have A1 of any assigned at runtime the value of D1 of type D, and we do a copy. Well, there is no name clash anymore, but to the version of copy that we had in any now correspond two versions in C. The feature C copy, which is really the same. It's the original one since it has not been redefined en route. So C copy is really copy, but now we have the one known as copy, which has been redefined. Note that it's a bit paradoxical in this case because the one which has the original name is not the same feature, it's been redefined, it's the one on the left. The one that is the same feature has a new name. So it's a bit paradoxical, but of course it's completely possible with this distinction between feature names and features. But now for something like A1, and sorry for the typo here, it should say A1 dot copy. For something like A1, we have an ambiguity. Are we going to use the list version or the C version, which is really copy from any? Of course, there is no general answer. The answer has to be determined by the programmer. And so the rule in this case is that if you have a replicated feature, meaning a feature that exists in two different forms as a result of renaming, then one of the versions should be selected as the one to be applied under polymorphism and dynamic binding, and this is our last clause, our last inheritance subclause, select, which by the way will go with rename, redefine, and so on. So you would say rename, then select, then redefine, and undefined. So we can say select copy and is equal in this case to say that we actually select these two features from their list branch rather than the C branch in order to resolve any ambiguity under dynamic binding. So this gives us the final rule for when a name clash is acceptable. It's actually very simple. They must all have, all the inherited features inherited under the same name must all have compatible signatures, and if more than one is effective, then they must all come from a common ancestor feature and a repeated inheritance, and then the select rule is going to apply. What we've seen in this segment is that repeated inheritance arises when a class inherits the same feature through more than one path. Renaming removes the confusion but leaves an ambiguity regarding application of the feature under polymorphism and dynamic binding. And to remove this ambiguity, we need to use select. This concludes the discussion of multiple inheritance, which now includes also repeated inheritance. I hope you are now convinced that it's a powerful modeling and programming mechanism which can also be used in a very simple and practical way and gives us a lot of power with mechanisms such as redefinition, renaming, undefinition, merging, and as we have now just seen, select.